Okay, so what I'm going to do is I'm going to go ahead and turn off my camera just so that hopefully, again, all the internet power goes into screen sharing so that we can get through this without any interruptions. I do have the chat open just in case you have any questions and you want to ask them while I am teaching. Completely up to you. You can ask them after if you want to go over something that I talk about. Today, we are going into constructing a two proportion z-test. So all of this is still going to follow that familiar pattern of phantoms. That's the big key idea for two proportion t- z-test. Sorry. We have defining the parameter, writing your hypotheses, checking your assumptions, naming the test, getting your test statistic, which is our z-score, obtaining a p-value, and then making a decision stating your conclusion. So all of the steps will be the same from our one proportion z-test, just slightly different because, again, we do have two samples. So we will start with defining the parameter. This is exactly the same as we did with the confidence interval for two proportions. We're going to have a P1, we're going to have a P2. Typically, this is up to you how you want to name and label them. The AP exam will have both possibilities of if, say, for instance, it's boys and girls. If you put group one as boys, group two is girls. And if you flip it and you did group two is girls and group one is boys. So they have all possible ways that you could be writing this as possible answers. And they're not going to mark it wrong just because you did girl boy and they did boy girl. Just for your peace of mind. Now, what's going to be different here is we're not going to have a null hypothesis. There is no value that we are necessarily saying these things are equal to. Instead, our null is that the true proportion of P1 is equal to the true proportion of P2. So that is always going to be our claim. Now, there's two different ways you could write this. You could write it saying P1 is equal to P2, or you could say P1 minus P2 is equal to 0, meaning that there's no difference in the two proportions. They're the same statement. It's just this is going to kind of explain how our formula gets created a little bit more. Sometimes they'll give you the null and alternative written this way. Just know it's not different. If I were to add P2 to both sides, I'm going to get this equation. Now, with that, there is a couple of different ways you can write your alternative hypotheses. So again, we have the less than, the greater than, the not equal to, the no difference. But following the other way you could write the null, we have the less than, the greater than, the not equal to. All of those kind of follow the same pattern of our one proportions. These are our three options. Remember, the not equal to is going to be something that has a statement in the question, like there's no difference between the two populations, or we don't expect to see anything that differs between them. It's not. And generally, they don't phrase it as not equal to, they just say that there's no difference. And then for here, for the less than, greater than, you'll have that kind of language to follow. So we would define our parameters, we'd state our null, we'd state our alternative. Then we are going to check assumptions and conditions. These are going to be the same exact assumptions and conditions as we did for confidence intervals. Now, there is one slight difference that I highlight here because a lot of the time when you're doing significance tests for two proportions, there is the possibility that you have created an experiment. And first thing, randomization. Either you selected both samples randomly or you have an experiment and there was random assignment to treatment groups. That also satisfies our random condition because it implements randomness into our samples. You have your 10% condition, population greater than 10 times the sample size. Generally, that's when we say, assume there are blank many people in the population. We have one other thing that we could also say, especially hand in hand with the idea that our randomness condition could be satisfied by random assignment to treatment groups. If you don't feasibly think that the 10% condition could be satisfied, that you don't know that your population is large enough, especially because we have smaller groups when we're doing experiments. If you don't think that this would be satisfied, you can also go into an independence condition that could replace the 10% condition. Basically, you would just try to say, they're not going to influence each other. Sample A is not going to influence sample B. There's no way that knowing one of them is going to affect the outcome of the other. And generally, that kind of goes hand in hand with experiments. Most of the time, we can get away with saying the 10% condition because it's going to be feasible. We can assume that there are that many people in the population. But in the instances where we can't, we're going to come in and we're going to say, assume that population A or the people, the samples are independent of each other. Only slight difference here. Success failure is exactly the same. We're going to do n times p hat greater than or equal to 10, n times 1 minus p hat greater than or equal to 10, just to make sure that I have enough successes and enough failures to assume an approximately normal distribution. Naming the inference method, almost the same, but it's going to be a 2-proportion z-test instead of a 1-proportion z-test or a 2-proportion confidence interval. You have a 2-proportion z-test. And then we have to get into the actual math calculation. So calculating the test statistic. So the null hypothesis for 2-proportion z-test states there's no difference between the two population proportions. We're saying that P1 is equal to P2. This is the null. So when I claim that, then my two populations should come from the same group. They should all come from the same place because I'm saying that they are equal to each other. So instead of using P1 or P2 separately, we use something called P pooled in the test. And this is going to be the general way how AP exam college board are going to look for an answer like this. So this is the formula that you would follow. So P pooled is actually taking all of these successes and all of the failures, or no, all of these successes and the entire sample size from both populations and combining them, pulling them together. So I have x1 plus x2 over n1 plus n2. So it's your total number of successes from both groups. And what I do is I plug that in generally where you would normally put your different p hats. I put them, this would be success, and then 1 minus p hat for P pooled would be your failures. And then similarly to the other formula for Z scores, we do 1 over N1 plus 1 over N2. It's just this is kind of distributing to both of them. This is the common way you will see it on your formula chart. One thing that I do want to kind of go over that so you don't think it's just a completely different formula than what you're used to, we usually do statistic minus parameter, where parameter is typically your P naught, your null proportion. Well, remember, if I have my null is P1 is equal to P2, that's the same thing as saying my null is equal to P1 minus P2 is equal to 0. So what I have is I have my statistic, my difference in the two populations, minus my null proportion, which is 0. That's my parameter. So the reason why we don't write it is because it's just like subtracting 0. And you really don't need to have it there because it's not going to do anything to your problem. But there is kind of like an imaginary minus 0 to satisfy the fact that we are subtracting the parameter in our typical normal z-square formula. I will say Most of the time, you're not going to be doing these by hand typically. Um, this is still something that we will be able to do in our calculator. I just always like to show you the formula just in case. Obtaining the p-value, same thing that we did with one proportion. You have to decide kind of what direction is my p-value area going. So if I'm doing less than, it's everything less than a z-score. Greater than, it's everything greater than a z-score. If I have a difference, then it's going to be on both tails, the lower tail and the upper tail. Here we calculate it by doing normal CDF. Now, one thing you have to be careful of if you are doing this by hand and you are going into normal CDF, the less than and the greater than are perfectly fine. Nothing special about them. But when you're doing the difference, there's no difference in the two populations. You have to remember to multiply it times 2. Find one of them. So in this example, I found the lower half. I did negative infinity to negative z and multiply it by 2. You could also go in and do a lower of z and a upper of positive infinity. It's going to give you the same exact value, but these two areas are equivalent. So find one, multiply it by 2. And this is only if you do it by hand. If you are doing it in your calculator already takes into consideration that there are two pieces and it reports that value already multiplied. So don't multiply it again when you're running the actual calculator test. So obtaining the p-value and then make a decision. It's the same idea. If it is less than, we reject. If it's greater than, we fail to reject the null hypothesis. The p-value is low, you reject the hoe. Easiest way to remember it. State the conclusion in context. It is going to be exactly the same since our p-value of whatever it is less than or greater than alpha. Typically, we assume alpha to be 0.05 unless we are told otherwise. We reject or we fail to reject the null hypothesis. There is or is not convincing evidence that whatever the alternative hypothesis is stating, that one is greater than the other or one is less than the other, or that there's no difference in the two. Plug in the context just to satisfy that checkbox for an AP exam for your response. Very, very important. So what we're going to do is we're going to go ahead and get into doing two examples together. First one I'm going to do by hand. Second one I'm going to show you how to do in your calculator, just so you can get a feel for both methods, figure out which one you enjoy and like more, and then kind of keep going that way. So example 1, Bridget, an AP statistics student, is curious to know if there is a difference in the proportion of male and female students who own an iPhone. So one thing I want to highlight, she wants to know if there is a difference in the proportion of male and female students who own an iPhone. When I see difference, that means I'm thinking my alternative is going to be not equal to. She takes an SRS of 90 females and 120 male students. So I have my 90 females, 120 males. The survey found that 61 females and 97 males owned an iPhone. Is there convincing evidence at the alpha equals 0.05 level that there is a difference in the proportion of females and males who own an iPhone? Convincing evidence is generally your big key giveaway that you are going to be doing a significance test. That's kind of the big words that they'll throw in there, especially if they give you an alpha. That's another big sign that you should be doing phantoms, hypothesis testing. That's the direction you want to go. Generally, for confidence intervals, they will state 95% confident or 98% confident. And that's your big key phrase to go the direction of panic. If they give you an alpha, go the direction of phantoms. So, first thing we're going to do is P, which is define our parameters. I have two groups. I have one group that is a male and one group that is a female. I said P1 is the true proportion of female students with iPhones. And I said P2 is the true proportion of male students with iPhones. So those are going to be my two groups that I'm trying to compare to each other. And once you have defined what your parameters are, you're now able to use them within your hypothesis, within your hypotheses. So my null is always that they're going to be equal to each other, no matter what the claim is, no matter what you're trying to test, no matter. It's always going to be that they are equal to each other. So I'm going to have my null is P1 is equal to P2. And my alternative in this case is Bridget's interested, is there a difference? So P1 not equal to P2. You do not have to write it in both ways. You could do the first method, or you could do P1 minus P2 is equal to 0. P1 minus P2 is not equal to 0. Pick one. Generally, my recommendation is this method on the left, just because it makes a little more sense in your brain. I'm saying that they're equal to or they're not equal to. Doing the extra step of moving it over tends to be a little bit confusing, but either way works, whichever one you prefer. So I have define my parameter, state my hypotheses. Now I'm going to go in and I'm going to check my assumptions. The first one is going to be my randomness assumption, and it states that she took an SRS of both 90 females and 120 male students. So I'm just going to say both samples are stated as SRS. And generally, when I'm not dealing with something where it's an experiment, I can most likely assume that there is enough people in the population to satisfy my 10% condition. So if I took 90 and I multiplied it by 10, I can assume that there are 900 females. And if I took 120 and multiplied it by 10, I can assume that there are 1,200 male students. So I can say assume at least 900 female and 1,200 male students are in the population. So that takes care of randomness, that takes care of 10%. The next one is going to be success fail. Now, this one's going to be a little bit different because they do have reported values for us. And because we are kind of unable to get a percentage, we don't necessarily have to calculate anything. If I were to take 61 over 90 and multiply that by 90, I'm still just going to get 61. So makes it a little bit easier on our end in terms of calculation. I have my females, I have my males. The success for females is 61, which is greater than 10. The fails for females is 29, which is greater than 10. My success for males is 97, which is greater than 10, and fails is 23, which is greater than 10. And since all of these conditions are met, since they're all satisfied, we can assume that we have an approximately normal distribution. And once all three conditions are checked, you can now go on into naming your test, calculating your test statistic, and all of that good stuff. Again, if one of the conditions happens to fail, you still want to move on with the test, especially on the AP exam. Typically, they aren't going to give you a question where all of the conditions aren't met, just because generally their path is to get you through a complete inference test somehow, some way. So if you do happen to have one fail, typically we make note of it. You can say fails, proceed with caution, or you can just write does not satisfy. And then in the conclusion, you would state something along the lines of, however, the 10% condition failed. Therefore, results may be inaccurate. Do not just stop if the condition is not met. Generally, not the right move. So I have my assumptions and conditions. I'm going to name my test. This is going to be a two proportion Z test. Now, the hand calculations for the Z score for this test are a little much. There's a lot going on. There's a lot of moving parts in that Z score formula. So the first thing I'm going to do, just for the sake of notes, is I'm going to rewrite it. This is the formula that's on the previous page. You don't have to write it all over again if you would not like to. I'm just putting it here for reference for us. So I need to know a couple of things. I need to know what P1 hat is, I need to know what P2 hat is, and I need to know what P pooled hat is. So I'm going to go ahead and start identifying those different things. Well, P1 hat is just our sample proportion. That's 61 over 90, which is approximately 0.6778. Just plugged it in my calculator, got my decimal answer, rounded it to 4 decimal places. P2 hat is 97 out of 120, which is approximately 0.8083. And then with my P pooled, what I do for that is I take my number of successes, which in our case was 61 and 97, and my sample size, which was 90 and 120, and I get approximately 0.7524. So when you're doing this by hand, there is a lot of things that go into it. There's a lot of moving parts, a lot of things you have to calculate in order to get the z-score formula by hand. So typically, this is one of those tests where I generally recommend going the calculator route only because there are a lot of steps where one number can kind of throw you off. So I have my P1 hat, P2 hat, P pooled hat. I know my N1 and my N2. That's not something I necessarily have to identify separately, but I know them 90, 120. Now I'm just going to take what I know and plug it into the formula. And what's going to be a little different here is you're going to get a very rounded answer. It's going to have a lot of steps where you rounded different things. We rounded P1 hat, we rounded P2 hat, we rounded the P pooled. So when you do this and you compare it to, say, you want to check your answer in the calculator, it may look slightly different. That does not necessarily mean it's wrong. If it's like way different, like you have point 0.5 and the calculator saying it's like 2.7, that would be something that's like a red flag. I would go back and double check everything. If it's something like where you have 0.156 and the calculator's telling you it's 0.162, not necessarily a big, huge difference, only because of the fact that there is a lot of rounding going on in these steps. So once I plug this into my calculator, I get z is approximately 2.1683, negative 2.1683. Now, when doing this by hand, you kind of have to do a direction. You have to decide what area is being shaded on a normal curve. Fortunately for us, this one doesn't require too much thinking because it is a difference alternative hypothesis, meaning no matter what, I'm going to have a lower tail, I'm going to have an upper tail. The z-score cutoff for both of these shaded regions is the same number. One is negative, one is positive. You only have to find the area of one of them. Does not matter which one. I believe I picked the negative one. Maybe, possibly. Oops. Yes. I went from negative infinity to negative 2.1683, mean of 0, standard deviation of 1. You're going to always have a mean of 0 and a standard deviation of 1 when you are working with z-scores all the time. So that makes my p-value approximately 0.0151, and that's only for one shaded region. So this area right here is 0.0151. But because they are the same cutoff value, that means the upper tail is also 0.0151. So all I have to do is multiply that by 2, gives me an approximate p-value of 0.0301. Lots of algebra in two proportion z-test, a lot more than the one proportion one. So I have my p-value. Last thing I have to do is interpret it. Good thing it's the same way we've been interpreting since we were doing one proportion. Since our p-value of 0.0301 is less than alpha, zero point zero 0.05, we reject the null hypothesis. The p-value is low, we reject the hoe. There is enough evidence to suggest a difference in the proportion of female and male students who own iPhones. So this was quite a doozy. It always seems very long, especially when you're doing two proportions and you're doing it by hand. I know some of us prefer to do it by hand, and that is absolutely okay. Just make sure you are correctly calculating your different samples just so that you don't get a small error. The nice thing about doing it by hand is that you do have reported values written down, and generally on the AP exam, they will give you some credit. If you just happen to maybe do 61 out of 100 for some reason on accident, or you switched your two sample sizes on accident, they can still give you credit for the rest of your work. The hard thing about the calculator is there's no way to know what you put in there. There's no way to know how your answer came to be what it was. There are some things they can kind of look at. That's why we write down the entire calculator output at the end. But generally, it's kind of just like up in the air. So, kind of a win lose in both situations, but just typically what you prefer. And if you happen to miss something that I am writing, I will post the filled in PDF at the end of the day for you to reference, just in case. Gonna give about another minute to finish writing up what's on the screen, and then we'll move on to our next question. Okay, example two should not take us as long just because we're gonna go calculator route this time, a little less algebra, which is gonna save us a lot of time. Assistant Principal, excuse me, Reams believes that pre-calculus teacher A is more effective than pre-calculus teacher B. An incoming class of 200 pre-calculus students are randomly assigned to two groups of size 100. One group is taught by teacher A and one group is taught by teacher B. At the end of the course, 60 of teacher A's students and 44 of teacher B's students pass the district exam. Do these results provide convincing evidence at the alpha equals 0.05 level that teacher A is more effective than teacher B? So we're trying to figure out, is teacher A more effective than teacher B? We have two samples. We have our, we're assigned to two groups of size 100. One group is taught by teacher A, one group is taught by teacher B, so each group has an N of 100. 60 of teacher A's students and 44 of teachers B students pass the district exam. So we kind of have our layout for what's happening. Now we have to go in and do phantoms. Again, big key thing, convincing evidence. They gave us an alpha level, big signs that you want to do a significance test. So I define P1 as the true proportion of teacher A's students who pass the exam. I define P2, true proportion of teacher B's students who pass the exam. And the alternative is going to be, is teacher A more effective than teacher B? So does she have more students who pass than teacher B? The null is always that they're equal to each other. And again, remember, you just have to pick one way to write it. It does not have to be both. I generally recommend the way on the left if I were you. HO is P1 is equal to P2. HA is P1 is greater than P2. So her proportion of students who are passing is greater than that of teacher B. So I have my parameters. I have my hypotheses. Now I need to go in and check my assumptions and conditions. Now this is a little bit different because technically I'm doing an experiment. I am assigning students to a teacher to see what the results would be. So I don't necessarily have an SRS. I was given 200 students. That's who I have. 200 pre-calculus students. I don't have a way to randomly sample those 200 students because it's just the incoming class. But I did introduce randomness by randomly assigning them to a teacher. So students were randomly assigned to a teacher. That satisfies our randomness condition. Now, with that being said, I only have 200 calculus students, pre-cal students. I don't have 100 times 10, 1,000 calculus students in this year. I don't have another 1,000 to satisfy the other one. But what I can say is the student performance is going to be independent, meaning one student is not going to affect the performance of another student in theory, as long as they're not cheating, which they should not be. But they don't have any result. Knowing that one student passes is not going to necessarily ensure that the other student passes. They are independent of each other. And again, typically with the way the significance tests get laid out, if you have to talk about random assignment in your randomness condition, typically you're going to use independence as your 10% condition. These kind of take the place of our normal way of satisfying these together. Just kind of the general pattern that we see. So success fail, I have teacher A, her success was 60, fail was 40. Both of those are bigger than 10. Teacher B, 44, 56. Both of those are bigger than 10, so we can assume a approximately normal distribution. Naming the test, a two proportion z-test. So once we have checked our conditions, we have our hypotheses, we've defined our parameters, named the test, now we can go into calculator steps. So I'm going to go ahead and put them on the screen. A lot of this you should be familiar with. You may not even have to write all of this down. I would write down how to get there. Stat tests, number 6. That's the one we're going to do. But the input is the same that we used for one proportion z-tests. Number of successes for group 1, sample size for group 1, number of successes for group 2, sample size for group 2, and then it's going to ask you what your alternative hypothesis is. So let's see, I'm going to open up my calculator. And I'm going to kind of go through the calculator steps with you. So first thing I'm going to do is I'm going to go to stat. I'm going to go over to tests, and I'm going to go down to number 6, my 2-prop z-test. With my 2-prop z-test, I'm going to press enter, and I have a lot of things in here that are not relevant to this question, so I'm just going to go in and, well, it's not going to let me delete it. I'm going to enter as I go. So the first thing is, what's your group 1? How many successes were in there? So I'm going to say group 1 was teacher A based on my parameter, and she had 60 successes out of, I believe, 100, because each group was 100 students. And then teacher B had 44 pass out of 100. And here you have to decide what's the alternative. So P1 is not equal to P2, P1 is less than P2, or P1 is greater than P2. This time we want is P1 greater than P2 based on the alternative that we wrote on our paper. Going to go down to calculate, and it gives us a lot of information. which makes sense because we had to find a lot of information to use the formula on example 1. So I have P1 is greater than P2. It gives me a z-score, gives me a p-value, gives me both sample proportions, gives me p pooled. So this is that PP hat that we had, sample size 1, sample size 2. So what I always like to do is take this entire thing and write it down on my paper. So I'm going to do that. I have z is equal to 2.2645, p is equal to 0.0118. I have all of my p hats. I have my two sample sizes. Took care of all of the algebra for this problem. Much quicker than doing it by hand. Last thing I have to do is put it into context, make my decision. My p-value is only 0.0118, which is less than my alpha. P-value is low. We reject the we reject the null hypothesis. There is enough evidence to suggest that pre-calculus teacher A is more effective than teacher B. So because of my p-value being low, we can say that we reject the null hypothesis and we can work with the idea that the alternative is true, that P1 is greater than P2. And this is the wrap up for two proportion z-tests. So what we will do on Wednesday is you'll get your review. I might post your review either tonight or tomorrow morning for the test this Friday. The test is only going to cover what we have learned since we have gotten back from Christmas break. I most likely will not have any one proportion tests on there. I will probably guarantee you'll at least see one two proportion z test, one two proportion confidence interval, just because we don't really have much that we covered since we got back. Just these two methods. You do have a MyLab assignment that accompanies this lesson. If you have not finished 6.7's MyLab, that's due at 11:59 tonight. If this assignment will be due 11:59 on Wednesday night. So if you haven't done 6.7 yet, I would do that first and then move on to today's practice. But other than that, have a wonderful Monday, guys. I will see you tomorrow. And I can stay on and move around if anyone missed anything on a previous page. But I will be here until 10 if you need help or you have any questions. So, Dylan, you're just going to have to do it in yours because I can't move you around. I will just go to your class period, your previous class period, and I'll pull your information from there. Everyone has the same times, due dates and due times. Bye, guys. Have a good day.